We're continuing with number systems, and this part is on binary arithmetic. Okay, we have talked about binary numbers, conversion to decimal. Then we also talked about codes, meaning that different numbers or different format for representing alphanumerics and things like that. But now we are going back to binary and focusing only on the arithmetic of it. Arithmetic will be only addition and subtraction. We are not going to be talking about multiplication because multiplication in a way is repeated additions. The same thing with division is repeated subtractions. So the focus mainly is on addition and subtraction. All right, let's take two 6-bit numbers, y6, just because the numbers I'm showing fit in 6 bits. Okay, in a few minutes, I'll talk about the size of the numbers, which we have to decide on a fixed length. And in the past, we talked about the 8-bit size, which we will also be sticking with that once we get into the arithmetic formats. All right, so let's, just for the sake of repeating what we have done in decimal or learning from decimal, let's do this in binary. Here, 1 and 1 is 0, and then there is a carry of 1. Okay, 1, 0, 0 is a 1, then there is a carry of 0. 0, 1, 0 is a 1, and then there is a carry of 0. 0, 1, 1 is 0, then there is a carry of 1 as shown here. Okay, 1, 0, 1 is a 0, then there is a carry of 1. Now I have a 1, a 0, that's a 0, and then I have a carry of 1, and then there is a 0 here, there is a 0 here, so it becomes 1 here. All right, so this is easy. I came up with the addition result of these two numbers. We can convert them to decimal to make sure that these are correct. I let you do it yourself. Let's go to the subtraction. It's going to be a little bit different. It's going to be a little bit more difficult. I'm subtracting 0. I'm doing this first, okay? I'm subtracting 0 from 1, and then I can do that, no problem with that. And then the result is 1, okay? I go on to the next position, and here I'm trying to subtract a 1 from a 0. Obviously, that is not doable. So what do? I borrow from the next position. Borrowing from the next position is adding a 1 to this, which translates to adding a 2 to this. Okay? So this is how I borrow. Now I have 1 subtracting from a total of 2. And therefore I have 1 from 2. I end up with a 1. Okay? So that's this one here. Let's go on to the next position. This position. What do I have? In this position, I have 1 plus 1, which is 2, which I'm trying to subtract from a 1. I cannot do that. 2 from a 1, I cannot do that. And therefore, I need to borrow again. A borrow becomes a 1 added here and translates to a 2 added here. Now let's look. I have 1 plus 1 is 2. I'm subtracting it from 1 plus 2, which is 3. Sure, I can do that. The result is 1. Let's go on to the next position. 1 plus 1 is 2. I'm trying to subtract it from a 1. Once again, I cannot do that. I need to borrow. The borrow becomes plus to the bit to the left, and then it becomes plus 1 to the bit to the left, plus 2 in this position, and therefore I have a 2 here, I have 3 here. 2, subtracting it from 3, I end up with a 1. Okay, let's go on to the left position, which is more significant position. Here I have 0 plus 1 is a 1. I'm trying to subtract it from a 0. I cannot do that. I have to borrow, and therefore I borrow a 2. That 2 translates to a plus 1 on the left position. Here I have 1 subtracting from a 2. Sure, I can do that. That's a 1. And now I go on to the next position. The next position is a 1 being subtracted from another 1 on top. I can do that. I end up with 0, and this is my result. Notice what happened. It was much easier to do the addition than subtraction. Okay? What it means is not only the procedure is different, but then if I want to build the hardware for it, there will be 2 pieces of hardware that are different. That means I have to build a hardware for addition. I have to build a different hardware for subtraction. We can avoid that. We can do something so that we use the same piece of hardware for addition and subtraction with some small changes. In order to do this, we have to learn subtraction by only addition. Or if there is a subtraction, it should be a simple subtraction. Since we are more familiar with base 10, let's do this in base 10. Okay? What I have is this. I'm trying to subtract 37 from 52. Okay? Let's say I don't want to borrow. Because if I want to do this, I have to borrow, right? Because this is 2, I cannot subtract 7 from 2, and therefore I have to subtract, I have to borrow. This becomes a 3 becomes a 4, and then this becomes 12. That's 5, that's 15. Okay? All right. Let's say we don't know this. I'm trying to subtract 37 from 52. Just for no good reason at all, I add 100, subtract 100. No problem, right? I add 100, subtract 100. Add 100, and then subtract 100. I'm not going to be looking at that minus 100 that seriously. Okay? So I kind of highlight it to kind of, at the end, perhaps ignore it. Okay? So let's look at this. I turn the plus 100 to 99 plus 1. So this has plus 100 became 99 plus 1. I take 37 and perform 99 minus 37 and then plus 1. So 99 minus 37 is an easy subtraction because 99 is the largest number with 2 digits, and therefore there is no borrowing. Okay? And therefore 99 minus 37, that's easy, becomes 62, just like this. Okay? So that becomes 99 minus 37 plus 1, that becomes 62. Plus 1. All right. And then the next step is 52 plus 63. Again, I'm not going to be looking at the minus 100 that seriously. 52 plus 63, I'm performing that addition. That becomes 115. Now, since this is 115, that's 1 digit more than the original 2 digits. I'm just going to ignore the last digit to the left. Okay? Actually, that compensates for that minus 100. And therefore, if I just ignore that 1 at the end, it's as if I'm subtracting from 100. And I'm not going to take that 100 very seriously. And at the end, I just drop the last one to the left. So let's see what really happened here. See, what happened here was, just clean this. What happened here was, instead of 52 minus 37, I added 52 plus 63, and ignoring the 100 and the 1 dropping and all that, adding 52 plus 63 gave me the result that I was expecting. Okay? So there's one interpretation. This is the result. There is one interpretation, and that is if I am adding 52 to 63 and I'm getting the result of 52 minus 37, perhaps 63 represents minus 37, which means this, which means that if A minus B, and then I am adding A to something and becomes the proper result. So what I have in parentheses must be minus B. And therefore this 63 is minus B. What kind of minus is this? This is a minus B in what is referred to as tens complement system. So this is negative 37 in tens complement system. And therefore, this is what we do. In order to perform subtraction in tens complement system, you look at the number of digits. Here we have 2 digits. You take the number you are subtracting from, or sorry, you take the number you are subtracting. Let's do an example. You have 532. You're subtracting from 499. Okay? What you do is you take the largest number in 3 digits, which is 999. You subtract 499 from it. That becomes a 0, that becomes a 0, that becomes 500. Then you add a 1 to it. Okay? So this becomes 501. So this becomes 532 plus 501. And then the result is, you perform the addition, is 3. It's 3 and 3, 10. Okay, or 1, 0. But then we decided that we are not going to be taking this one so seriously, so drop it. And therefore what I have is, I am performing this subtraction. The result is 33. And I didn't do any borrowing in this calculation. Then I refer to 501 as the tens complement of 499. That's why adding 532 to 501 gives me the result of subtraction of 532 minus 499. Now that we know this, let's do the same thing in the binary system. Okay? So that this becomes clear, we have actually found a new way to negate 37, and that is by subtracting it from 99 and adding a 1 to it. Let's do the same thing with binary numbers, but then here we have to, the same way we started with 2 digits, here we have to start with certain fixed number of digits. We also expressed this before. We said this before. We said that when you are representing binary systems, binary numbers, you have to know the length. See, when I'm writing numbers on paper, I can add as many zeros to the left as I want. Okay, so if I am adding 39 plus 96, I say, okay, fine, 5 and then 13, and then I added a 1. So I added 2 digits, it became 3 digits. But then if you have binary numbers inside the computer system, inside the digital system, these binary numbers, you cannot just expand the number as you wish, because there are bus sizes, there are register sizes, there are hardware sizes that can only give you 8 bits, maybe. Or they can only give you 16 bits. And therefore, when we are doing arithmetic in binary, we have to consider the word length, or the length of the number. Here I'm dealing with 8 bits. Okay? For now. And then we talk about larger number of bits later. Here I'm subtracting 0, 0, or I'm performing this subtraction. 0, 0, 1, 1, 0, 1, 0, 0, minus 0, 0, 1, 0, 0, 1, 0, 1. Okay? What I do is I add in 8 bits, the largest number in 8 bits is 8 ones plus a 1. That becomes the number I yellowed right now. Okay? And then I subtract it from, obviously, the arithmetic will not be correct if I just add this. I subtract it from this, which I'm not going to be taking too seriously. Okay, so this is not going to be taken too seriously. This is not going to be taken too seriously. Same here. And then I show you what effect it has later on. All right, so what I'm doing is performing this subtraction, and I added 8 zeros, and the next step is I break down the 8 zeros to, I break it down into all ones plus 1. I perform 1, 1, 1, 1, 1, 1, 1, 1, minus 0, 0, 1, 0, 0, 1, 0, 1. Okay? That's an easy subtraction. Like in the previous case, in the decimal case, what I did was I was subtracting 37 from 99. There is no borrowing there. So neither there is borrowing here. So let's perform this subtraction. Actually, this is even easier than decimal, because all there is to it is complementing every bit. Okay? 1 minus 1 is 0, 1, 0, 1, 1, 0, 1, 1. Okay? But then I have to add a 1 to it. No problem. Adding a 1 is easy. And this becomes 1, 1, 0, 1, 1, 0, 1, 1. Which is this number. Okay, now look at this. Again, don't take the red part too seriously. What I'm doing is I have, this is my number A. I'm performing A minus B. But then on this line here, A is A. I'm not touching A. But then I have, well, let's 0, 0, 1, 1, 0, 1, 0, 0. Okay. And then I have 1, 1, 0, 1, 1, 0, 1, 1. Okay. I'm adding. Since I'm adding here, and this is the same number I have on this lower right hand side. Let's do the adding. There is a 1 here, there is a 1 here, there is a 1 here, there is a 1 here. 1 and 1 is 0, 1, 0, 1, 0, 1, 0. Then I get a 1. Okay? Which is this. And then I have an extra 1, which I decided that the same way I'm not taking the -1 all zeros too seriously, I'm not going to take this too seriously either. Actually, they compensate. So the subtraction of the 100001111 minus 180 becomes this. But then if I say the -1 zeros, let's not take it too seriously. Neither take a digit beyond 8 too seriously. Okay? So what it means is, if you get the digit beyond the 8th digit, ignore it. The same way you are ignoring -1 bunch of zeros. What I have here is exactly the same thing we did before, which is I'm doing A minus B. This is still A. And then I'm adding it to something, which the result becomes A minus B. That means this something, that green area here, is a minus B. What kind of minus B is this? This minus B, the same way the in the previous one, 63 was tens complement in tens complement system. This minus B is in twos complement system. So we reached a procedure. The procedure is the following. Instead of subtracting, turn B into its twos complement representation. How do we do this? Complement all the bits, add a 1 to it. And then perform addition. If you get an extra bit to the left, just drop it, forget it. Okay? This is twos complement system. Remember that we also talked about sign and magnitude system. If we were to do sign and magnitude system, that wouldn't be that easy. Sign and magnitude, you had to look at the sign, you had to either perform addition or subtraction depending on the sign of the numbers you are subtracting or adding to. But here, I don't really care. Okay? If I have a subtraction, I turn the number to its twos complement. If it is a negative number, it becomes a positive number. If it's a positive number, it becomes a negative number. Look at this, for example. If this was my B, I'm going to write it in a different color to separate it from this. So if it was something like, for example, this, 0, 1 0 0 1 0 0 1. Okay, that's an 8-bit positive number, and I am subtracting it from this number. Well, this number is a negative number. Okay, because as with the sign and magnitude case, the leftmost bit is still representing sign bit. And therefore, instead of this subtraction here, what I do is I keep A as A, negate B. 0, 1, 0, 0, 1, 0, 0, 1. Negate B. B negating B means that complemented becomes 0, 0, 0, 1, 0, 1, 1, 0. Add a 1 to it, becomes 0, 0, 0, 1, 0, 1, 1, 0. I negated it. And now I perform addition instead of subtraction. This becomes a 1, a 1, a 1, a 1, a 1. I didn't really want this to become all 1, but this is how it turned out to be 0, 1, 0. And therefore, the result of the subtraction I'm showing in blue becomes this. Okay? So I have a new representation for my negative numbers, and I have a new procedure for adding and subtracting. The system 2's complement system is going to be used throughout this course, and every time you're doing hardware, 2's complement is the key thing, is the main thing for representing negative numbers, negative and positive numbers. So when I say this, this is an important to note. When I have this situation, this is an 8-bit positive number, an 8-bit positive number in 2's complement system. This is an 8-bit negative number in 2's complement system. Okay, how do I know it's a negative number? Because the leftmost bit is a 1. How do I know the one on top is a positive? Because the leftmost bit is a 0. It turns out that positive numbers in 2's complement system and sign and magnitude system look exactly the same. I cannot say this about negative numbers. Negative numbers in sign and magnitude and in 2's complement system look different. All right. I can do this a little bit easier. Instead of saying that, instead of doing what I said, which is complementing and adding a 1 to it, see? Okay. Complementing and adding a 1 to it means that complementing becomes 0, 1, 1, 0, 1, 1, 0, 1. Adding a 1 to it becomes, need a little bit space here, 0, 1, 1, 1, 0, 1, 1, 0. Instead of doing this, I can do this a little bit easier. I can say, let's just start from the right-hand side. Copy everything as is until the very first one from the right-hand side. So this is repeated as is, this is put in as is, and then anything to the left will be complemented. 1, 1, 0, 1, 1, 0. Okay? That's a different procedure for turning a positive number to its 2's complement, or a negative 2's complement number to its positive equivalent, meaning converting 2's complement numbers. So if this is 0, 0, 1, 0, 1, 1, 1, 1, which is 32, 47. This is 47. Okay, let's do 46. This is 46. Minus 46 is this. Start from the right-hand side. 0, 1. Write down everything, including the very first one from the right-hand side. Everything from then on gets complemented. This is 0, 0, 1, 0, 1, 1. So if the above is plus 46, what I'm showing below is minus 46. So basically, what you read over here is the same thing I've been saying. 2's complementing a number consists of complementing and adding a 1 to it. And you go from positive to negative or negative to positive. For example, if I give you this number and tell you that this number is 1001001, and tell you that this is a 2's complement number, tell me what the positive of this is, you would do, write the first one as is, start from the right hand side, write all the ones as they are until the very first one. It turns out the very first one is the first digit. And then complement everything else. 0, 1, 1, 0, 1, 1, 0. Okay. What is this? This is 1, 4, 8, 16, 32, 64. That's 9600. This is 109. And therefore, this is minus 109. Okay? And so this rule that I just said is I put this in yellow. And so these are 2's complement numbers. Here are a few examples. I'm adding 27. And then for now, I'm doing everything in 8 bits. I have to have a fixed length if I'm going to talk about sign bit, because the sign bit is the leftmost bit. Okay? And therefore, I have to know the size of it. This is 27, this is 77. Let's add them together. And I'm doing in 2's complement system. It turns out both of them are positive, and therefore I don't have to do anything different. 1 and 1 is 0. A carry of 1, 0, 1, 0, 1, 1, 1 is 1. A carry of 1, 1, 1, 0, 1, 1. And a carry of 0, 0, 0, 1. A 1, a carry of 0, and my result becomes this. Okay? Hopefully, this is 104. Do you want to know what minus 104 looks like? Here. 0, 0, 0, 1, and then 1, 0, 0, 1. This is minus 104. Okay? Just so that you see the conversion. I didn't need it here. All right. Let's look below. Here I have 0, 0, 0, 1, 1, 0, 1, 1. I'm subtracting 0, 1, 0, 0, 1, 1, 0, 1 from it. Okay? I'm subtracting this from it. What it means is I have 27 minus 77. Okay? I can go back to that negating thing, the borrowing thing, and perform this subtraction. But then I said, well, no, I have a better way of doing it. What I do is I take minus 77 and turn it into its 2's complement. 77, turn it into its negative in 2's complement system. It becomes a 1, a 1, a 0, a 0, a 1, a 1, a 0, a 1. Okay? That becomes minus 77. So what I do is I add 27. This is 27. This is minus 77. I add these two together. And then the result is 1. I'm just adding exactly as if I'm adding. But then the result becomes subtraction. 1, 1, 0, 1, 1, 1, 1 is 1, 1, carry. A 1, a carry of 0. A 1, a carry of 0. 1, 0, 1, 1 is a 0. A carry of 1, 0, 1, 1, 1. Okay? That becomes my result. Obviously, it's a negative number because I'm subtracting 77 from 27. But then, what is it? Well, in order to know what it is, turn it into its 2's complement, because this is a negative number. Turn it into its 2's complement, becomes a positive number. Start from the right-hand side, repeat everything that there is, 0 and 1, and then complement everything to the left, 1, 1, 1, 1, 0, 0. And therefore, you look at this number, this is 50. Here, 1, 2, 4, 8, 16, 32, that's 48, and 2 is 50. Okay? Things are not always as rosy as I'm showing it here. Okay. What if, let's look at these two numbers. What if I have a situation that I'm adding these two, and then remember, this is the sign bet. 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, a 0, and a 1, 1, 0, 1, a 0, a carry of 1, 1, 0, 0 is a 1. This is a positive number, A. This is a positive number, B. The result is a negative number. What is this telling me? It is telling me that the 8 bits that I gave my numbers is not enough for representing the sum of these two numbers, and I refer to this as overflow. I have an overflow situation. Overflow means this, means that the space you are giving these numbers is not enough. So what do? Well, switch to the next level up, meaning if you are doing 8-bit arithmetic, turn it into 16-bit arithmetic. If you're doing 16-bit arithmetic and then you need more space, do 32-bit arithmetic. So a negative number has occurred because, and then I'm adding two positive numbers. This is not good. And if I really want to represent this with the minimum, I need 9 bits, but I don't do 9 bits. Okay? In a system, I don't do 9 bits. I either go from 8 to 16 or 16 to 32. Okay? I cannot just add wires as I wish. All right. Let's do another overflow situation. Here I have this number, a negative number, 8-bit. And then here's another negative number. Okay. Let's add them together. These are both 8-bit negative numbers in 2's complement system. 1 and 1, 0, carry of 1. 1, 1, 0, 0, carry of 1. 1. 0 and 1 is a 1, carry of 0. 0, 1, 0 is a 1, carry of 0. 0, 0, 1 is a 1, carry of 0. This is 0, 1 and 1 is 0, and then I have a last 1. This is 8-bit. This is requiring 9 bits. I'm not going to give it 9 bits. I just say, well, this is an overflow situation. Okay? You want to resolve this overflow situation? Well, this is what you can do. You can look at the numbers and say, well, in order to avoid overflow in this situation, let's keep the numbers. If these are the numbers, let's give them more space. So instead of saying that I want to have 1, 0, 0, 1, 0, 0, 1, 1 in 8-bit, represented in 16 bits. So what I do is the first number becomes 1, 0, 0, 1, 0, 0, 1, 1. And then the second number, 1, 0, 1, 0, 1, 0, 0, 1. I want to turn it into 16-bit. But then the 16-bit has to be a 16-bit 2's complement number. And bit number 15 all the way to the left has to be a 1. Okay? I'm not just going to put zeros on the left. I'm going to take the sign and extend it all the way to the left. So I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now I have given them more room. I have given them 16 bits. 1 on 1, 0, 1, 0, 1, 1, 1, 1, 1, 0. Now look at this. 1 and 1 is 0. A 1, 1, 1, 1, 1, 1, 1, 1, 1. And I get a final 1. What do I do with this one? Don't worry about it. That's the 100 that we added. The one that I said don't take it too seriously. Drop it. Now I am adding two negative numbers. Here. I'm adding two negative numbers, and the result is a negative number. Unlike this situation that I was only giving it the two numbers 8 bits. Now I'm giving it 16 bits. This is called sign extension. And you do sign extension when you need more space, and sign extension if it's a positive number, zeros will be repeated. If it is a negative number, ones will be repeated, which is the sign itself. And this is how you avoid overflow. And here is sign extension for extension. Okay. This is sign extension for positive numbers. Look here, 1, 2, 3, 4, 5, 6, 7, 8. This is a positive number. This is a positive number. And when I was adding these two, I got an overflow, and therefore the result was a negative. That's the first example I was doing before here. This one here. Okay. And in order to avoid this, I perform sign extension. This is the sign, this is the sign, extend it all the way to the left. Same thing with this. Okay, now you are adding these two 16-bit numbers. This becomes the sign, not this. And therefore, now what you have is two positive numbers. The result is positive number. No problem with that. Nobody complains. All right. What we have covered: binary number representations, binary to decimal, decimal to binary, and then we have done coding system, BCD, gray code, and a few other coding systems. Then we do binary arithmetic and 2's complement system, which is a good system for arithmetic. Okay, if you only want to have numbers represented so that you know this is positive or negative, and you are not going to do arithmetic, perhaps sign and magnitude is better. Okay, this is it with the number system.